A small moon is spraying its ocean directly into space. Right now, as you listen to these words, geysers of water are erupting from cracks near the south pole of Enceladus, Saturn's sixth largest moon. The plumes rise hundreds of kilometers above the surface before falling back or escaping into the void. Some of this water forms a diffuse ring around Saturn, some drifts outward into interplanetary space, and some was captured by a spacecraft named Cassini, which flew directly through the spray and analyzed what it found. The results changed everything we thought we knew about where life might exist in our solar system. Enceladus is tiny. At just over 500 kilometers in diameter, it would fit comfortably inside the state of Arizona. It orbits Saturn at a distance of 240,000 kilometers, completing one orbit every 33 hours. From Earth, it appears as nothing more than a faint point of light near the ringed planet. Yet this insignificant speck of ice has become one of the most important targets in the search for extraterrestrial life. Beneath its frozen surface lies a global ocean of liquid water. At the bottom of that ocean, hydrothermal vents may be pumping heat and chemicals into the darkness. And the moon itself is offering us samples, shooting material from its hidden sea into space where we can collect and study it. No drilling required, no landing necessary. Enceladus is handing us its ocean on a silver platter. Today we will explore this remarkable world. We will trace the history of its discovery and the missions that revealed its secrets. We will examine the evidence for its subsurface ocean and the chemistry that makes it potentially habitable. And we will consider what it would take to find life there, if life exists. The story of Enceladus begins in 1789, during the golden age of telescopic astronomy. William Herschel was the greatest observational astronomer of his era. A German-born musician who had emigrated to England, Herschel built his own telescopes, grinding mirrors by hand to achieve unprecedented clarity. In 1781, he had discovered Uranus, the first new planet found since ancient times. The discovery made him famous and earned him a royal pension, allowing him to devote himself entirely to astronomy. Herschel was methodical. Night after night, he swept the sky with his telescopes, cataloguing everything he saw. Nebulae, star clusters, double stars and moons. He was particularly interested in Saturn, which had fascinated astronomers since Galileo first saw its rings in 1610. On August 28, 1789, Herschel was observing Saturn with his newest and largest telescope, a monster with a mirror 48 inches in diameter. Near the planet, he noticed a tiny point of light that moved from night to night. It was a new moon, the sixth to be discovered orbiting Saturn. Herschel did not name his discovery immediately. For years, it was simply referred to as Saturn's sixth satellite. The name Enceladus came later, suggested by Herschel's son John, who proposed naming Saturn's moons after the Titans of Greek mythology. Enceladus was a giant who had rebelled against the gods and was buried beneath Mount Etna as punishment. According to legend, his struggles caused earthquakes and volcanic eruptions. The name proved prophetic, though no one could have known it at the time. For nearly 2 centuries, Enceladus remained a mystery. Telescopes could reveal nothing more than a point of light. Astronomers could calculate its orbit and estimate its size, but its surface, composition, and geology were completely unknown. The first real data came from the Voyager missions. In 1980 and 1981, the twin Voyager spacecraft flew through the Saturn system, returning the first close-up images of the planet its rings, and its moons. Voyager 1 passed within 200,000 kilometers of Enceladus, too distant for detailed imaging. But Voyager 2 came much closer, approaching within 87,000 kilometers in August 1981. The images revealed a world unlike any other moon in the solar system. Most icy moons are heavily cratered, their surfaces scarred by billions of years of impacts. Enceladus was different. Some regions were cratered, yes, but others were almost completely smooth. Vast plains showed few or no impact craters, suggesting they were geologically young. Something had resurfaced these areas recently, erasing the evidence of ancient bombardment. Even more intriguing were the fractures. Long, linear cracks crossed the surface, some stretching for hundreds of kilometers. These were not random. They showed patterns suggesting tectonic forces, as if the moon's crust was being stretched and compressed by some internal mechanism. Voyager also revealed that Enceladus was astonishingly bright. Its surface reflected nearly all the sunlight that hit it, making it the most reflective body in the solar system. Only fresh, clean ice could be so bright. Something was constantly renewing the surface, keeping it free of the dark dust that accumulates on most airless bodies. The Voyager scientists were puzzled. Enceladus was far too small to retain internal heat through radioactive decay alone. Where was the energy coming from to drive geological activity? Some suggested tidal heating, the flexing of the moon's interior caused by Saturn's gravity. But the calculations were uncertain and the evidence was limited. The mystery would remain unsolved for another quarter century. In 1997, NASA launched the Cassini-Huygens mission to Saturn. It was one of the most ambitious planetary exploration projects ever attempted, a collaboration between NASA, the European Space Agency, and the Italian Space Agency. The mission had been decades in the making. Scientists had proposed Saturn orbiters since the Voyager flybys revealed how much remained to be discovered. Budget battles, technical challenges, and changing priorities delayed the project repeatedly. But persistence paid off, and Cassini finally launched on October 15, 1997, from Cape Canaveral. The spacecraft was massive by planetary exploration standards, weighing over 5,000 kilograms fully fueled. It stood nearly 7 meters tall and carried 12 scientific instruments on the orbiter alone, plus 6 more on the Huygens probe. The instrument suite could measure magnetic fields, analyze particles and dust, image surfaces in multiple wavelengths, and determine the chemical composition of atmospheres and surfaces. Power came from 3 radioisotope thermoelectric generators containing about 33 kilograms of plutonium dioxide. These generators would provide electricity for the entire mission, slowly declining from about 800 watts at launch to around 600 watts by mission's end. The spacecraft consisted of 2 parts. Cassini was an orbiter designed to study Saturn, its rings, and its moons over many years. Huygens was a probe that would descend through the atmosphere of Titan, Saturn's largest moon, and land on its surface. The journey to Saturn took nearly 7 years. Cassini used gravity assists from Venus, Earth, and Jupiter to gain the speed needed to reach the outer solar system. It flew past Venus twice, in April 1998 and June 1999, gaining energy from each encounter. In August 1999, it swung past Earth at an altitude of 1,200 kilometers, a maneuver that caused some controversy due to the radioactive material on board. In December 2000, Cassini passed Jupiter, receiving a final gravitational boost and conducting scientific observations of the giant planet. It captured the most detailed global portrait of Jupiter ever made, a mosaic of images that revealed storms, cloud bands, and the Great Red Spot in unprecedented detail. Finally, on July 1st, 2004, Cassini fired its main engine for 96 minutes, slowing itself enough to be captured by Saturn's gravity. It was a tense maneuver. The engine had to perform flawlessly after 7 years in space. A failure would have meant the spacecraft would sail past Saturn and be lost forever. The burns succeeded perfectly. Cassini entered orbit and immediately began returning stunning images of Saturn, its rings, and its moons. The first close-up views of the rings revealed structure upon structure, waves and gaps and spokes that told of gravitational interactions with Saturn's many moons. On December 25, 2004, the Huygens probe separated from Cassini and began its journey to Titan. 3 weeks later, on January 14, 2005, Huygens entered Titan's atmosphere and descended by parachute through the orange haze. It transmitted data for over an hour during descent and continued for another 72 minutes after landing, revealing a frozen landscape of pebbles made of water ice beneath an orange sky. But it was another moon that would prove most surprising. The primary mission was planned for 4 years, but Cassini proved so successful that it was extended twice. The spacecraft ultimately operated for 13 years, revolutionizing our understanding of the Saturn system. Among its many discoveries, none was more surprising than what it found at Enceladus. Cassini's first close flyby of Enceladus occurred in February 2005. The spacecraft passed within 1,200 kilometers of the surface, close enough for detailed imaging, but not close enough for what would come later. The images confirmed and extended Voyager's findings. The surface was indeed young in many places, with smooth plains and complex fracture systems. The South Polar region was particularly interesting, dominated by 4 roughly parallel fractures that scientists nicknamed the tiger stripes. These features, each about 130 kilometers long and spaced about 35 kilometers apart, were warmer than the surrounding terrain. How could parts of a tiny frozen moon be warm? The answer came 3 months later. In July 2005, Cassini's magnetometer detected something unexpected. The moon appeared to have a significant effect on Saturn's magnetic field, far more than a simple ball of ice should produce. Something was happening at Enceladus, something that was releasing material into space. Mission controllers quickly adjusted Cassini's trajectory to pass closer to the moon on subsequent flybys. In November 2005, the spacecraft swooped within 173 kilometers of the surface and captured images that stunned the scientific community. Enceladus was erupting. Giant plumes of water vapor and ice particles were shooting from the tiger stripe fractures, rising hundreds of kilometers above the South Pole before dispersing into space. The geysers were enormous, visible against the blackness of space like fountains of diamond dust. Nothing like this had ever been seen before. Other bodies in the solar system have volcanic activity. Io, Jupiter's innermost large moon, is covered with sulfur volcanoes. But Enceladus was spewing water, not lava. It was cryovolcanism on a scale never previously observed. The discovery immediately raised 2 questions. Where was the water coming from? And what was providing the energy to eject it into space? Over the following years, Cassini made more than 20 close flybys of Enceladus, some passing within 50 kilometers of the surface. Each encounter added new pieces to the puzzle. The plumes emerged from the tiger stripe fractures, which scientists formally named sulci: Alexandria sulcus, Cairo sulcus, Baghdad sulcus, and Damascus sulcus. The fractures were about 500 meters wide and up to 500 meters deep, with raised edges like the lips of healing wounds. Infrared measurements showed that the tiger stripes were significantly warmer than the surrounding ice. Temperatures along the fractures reached -80 degrees Celsius, which sounds cold, but is more than 100 degrees warmer than the ambient surface temperature. Something was heating the ice from below. The total heat output from the South Polar region was estimated at about 5 gigawatts, equivalent to a dozen large nuclear power plants. This was far more than could be explained by radioactive decay in Enceladus's rocky core. The heat had to come from tidal flexing. To understand tidal heating, consider what happens as Enceladus orbits Saturn. Saturn's immense gravity raises tidal bulges on Enceladus, stretching the moons slightly along the line connecting their centers. If Enceladus's orbit were perfectly circular, these bulges would stay fixed and no energy would be dissipated. But Enceladus's orbit is not circular. It is slightly elliptical, thanks to a gravitational resonance with another moon, Dione. For every orbit Enceladus completes, Dione completes exactly half an orbit. This resonance pumps energy into Enceladus's orbit, maintaining its eccentricity against the forces that would otherwise circularize it. Because the orbit is elliptical, Enceladus's distance from Saturn varies throughout each orbit. When closer to Saturn, the tidal bulges are larger. When farther, they are smaller. This means the bulges are constantly growing and shrinking, flexing the moon's interior. Flexing generates heat through friction. Ice crystals rubbing against each other, rock fragments grinding together, and viscous deformation of partially molten regions all convert mechanical energy into thermal energy. This tidal heating is concentrated in regions where the ice is already warm and pliable, which in turn makes those regions warmer, creating a feedback loop. The South Polar region of Enceladus experiences the strongest tidal stresses. The ice shell is thinnest there, perhaps only a few kilometers thick, and the tiger stripe fractures may extend all the way through to the ocean. Heat flows upward from the warm interior, keeping the fractures open and powering the geysers. This mechanism explains why Enceladus is active despite its small size. Tidal heating does not depend on the moon's mass or radioactive content. It depends on the orbital dynamics, the eccentricity of the orbit, and the strength of the gravitational forces. Enceladus happens to be in the right configuration to experience significant tidal heating. The same mechanism operates on other moons. Io, Jupiter's innermost large moon, experiences extreme tidal heating that drives hundreds of active volcanoes. Europa experiences gentler tidal heating that maintains its subsurface ocean. Enceladus falls somewhere in between, with enough heating to maintain an ocean and power cryovolcanism, but not enough to turn the moon into a volcanic hellscape. As Enceladus orbits Saturn, its distance from the planet varies slightly due to gravitational interactions with other moons, particularly Dione. This causes the tidal bulge raised by Saturn's gravity to shift back and forth, flexing the moon's interior. The flexing generates friction, and friction generates heat. But tidal heating alone could not explain the plumes. Water would need to be liquid to erupt as geysers. Where was this liquid water? The answer emerged gradually through multiple lines of evidence. First, there was the composition of the plumes. Cassini carried instruments capable of analyzing the material it flew through. The plumes were about 98% water vapor, but the remaining 2% was revealing. Carbon dioxide, methane, ammonia, and various salts, including sodium chloride, ordinary table salt. Salt was the key. Salt in the water meant the plumes were not simply ice sublimating from the surface. They had to originate from liquid water that had dissolved minerals from rock. This pointed to a subsurface ocean in contact with a rocky sea floor. There was another clue hiding in plain sight, one that astronomers had puzzled over for decades: Saturn's E-ring. Saturn has many rings, from the brilliant main rings visible in any telescope to faint, tenuous structures that require spacecraft to detect. The E-ring is one of the outermost, a broad, diffuse band of particles extending from the orbit of Mimas to well beyond the orbit of Titan. Unlike the main rings, which are composed of chunks of ice ranging from dust grains to house-sized boulders, the E-ring consists primarily of very small ice particles, just a few micrometers across. These particles are so small that radiation pressure and other forces should disperse them within a few hundred years. Yet the E-ring persists. Something must be constantly replenishing it. That something is Enceladus. The Moon orbits within the densest part of the E-ring. The plumes eject roughly 200 kilograms of material into space every second. Most of this falls back to the surface or remains in Enceladus's immediate vicinity, but a significant fraction achieves escape velocity and enters orbit around Saturn, feeding the E-ring. Cassini confirmed this connection directly. The composition of E-ring particles matched the composition of Enceladus's plumes. The particle sizes were consistent with formation in the geysers. The spatial distribution showed a clear concentration around Enceladus's orbit. Enceladus is not just a moon with geysers. It is a moon that is actively creating a planetary ring. This is happening right now, in real time, a geological process visible on human timescales. The E-ring particles gradually spiral inward under the influence of radiation pressure and plasma drag, eventually falling into Saturn's atmosphere or being swept up by inner moons. The ring exists in a dynamic equilibrium, constantly replenished by Enceladus and constantly depleted by physical processes. This realization put the plumes in a new perspective. They were not a minor curiosity, but a major feature of the Saturn system, influencing the environment throughout the region between Saturn and Titan. Second, there was the behavior of the plumes themselves. The eruptions varied in intensity depending on where Enceladus was in its orbit. When the Moon was farther from Saturn, tidal stresses pulled the tiger stripes open wider, and the plumes intensified. When closer to Saturn, the fractures compressed and the plumes weakened. This tidal modulation suggested the plumes were controlled by mechanical opening and closing of vents connected to a liquid reservoir below. Third, there was gravity data. By tracking tiny changes in Cassini's velocity as it flew past Enceladus, scientists could map variations in the Moon's gravitational field. These measurements revealed a mass concentration beneath the south polar region, consistent with a sea of liquid water denser than the surrounding ice. Initially, scientists thought the ocean might be limited to the south polar region, a local sea beneath the active zone. But further analysis told a different story. Enceladus wobbles slightly as it orbits Saturn, a motion called libration. The amount of wobble depends on how the Moon's mass is distributed internally. If Enceladus was solid ice all the way through, it would wobble less. If it had a liquid layer decoupling the surface from the core, it would wobble more. Cassini's measurements of this wobble were unambiguous. Enceladus wobbled too much to be solid. The ice shell had to be floating on a global ocean that surrounded the entire Moon. The ocean is estimated to be about 10 kilometers deep on average, though it may be much deeper beneath the South Pole, where the ice shell is thinnest. The ice shell ranges from about 30 kilometers thick at the equator to perhaps 5 kilometers or less at the South Pole. Below the ocean lies a rocky core roughly 400 kilometers in diameter. This is remarkable. Enceladus is only 500 kilometers across, yet it contains a liquid water ocean larger in volume than all the Great Lakes of North America combined. And this ocean has probably existed for millions or even billions of years. But the most exciting discovery was yet to come. In 2015, Cassini made its deepest dive through the plumes, passing within 49 kilometers of the surface and flying directly through the densest part of the spray. The spacecraft's instruments detected something that made astrobiologists sit up and take notice: molecular hydrogen. Hydrogen gas was streaming out of Enceladus along with the water vapor and ice. This was not a trivial finding. Hydrogen is the fuel of life. On Earth, certain microorganisms called methanogens combine hydrogen with carbon dioxide to produce methane and energy. They need no sunlight. They need no oxygen. They need only hydrogen, carbon dioxide, and water. Such organisms live today at hydrothermal vents on the ocean floor, at hot springs in volcanic regions, and in the deep subsurface of continents. Where was the hydrogen coming from? The most likely explanation is serpentinization, a chemical reaction between water and certain types of rock. When water interacts with minerals containing iron and magnesium, such as olivine, it produces serpentine minerals and releases hydrogen gas. The reaction also generates heat, contributing to the thermal budget of the ocean. Serpentinization requires liquid water in contact with hot rock. The detection of hydrogen strongly suggests that Enceladus has hydrothermal vents on its ocean floor, places where hot, chemical-rich water emerges from the rocky core. This was the missing piece. Enceladus did not merely have a subsurface ocean. It had an ocean with a rocky sea floor, hydrothermal activity, chemical energy, and organic molecules. It had, in short, all the ingredients that astrobiologists believe are necessary for life. Cassini also detected complex organic molecules in the plumes, compounds containing carbon chains with multiple atoms. These were not proof of life. Such molecules can form through purely chemical processes, but they showed that the ocean contains the building blocks from which life could potentially arise. The silica nanoparticles were equally significant. Cassini detected tiny grains of silica, just nanometers in size, in the plume material. On Earth, silica particles of this specific size form only under specific conditions. Hot water, at least 90 degrees Celsius, interacting with rock and then cooling rapidly. This suggested that water temperatures at the core ocean boundary reach at least 90 degrees Celsius, possibly much higher. Hot water rises from the sea floor, carries dissolved silica upward, and cools in the overlying ocean, precipitating the nanograins detected by Cassini. Put all the evidence together, and a picture emerges of an ocean far more dynamic and potentially habitable than anyone had imagined possible on such a small, cold moon. Let us take an imaginary journey to the depths of Enceladus. We descend through the tiger stripe fractures, passing through the chaotic zone where ice meets void and geysers erupt into space. The walls of the fissure are coated with fresh ice crystals, constantly replenished by the upwelling spray. Light from Saturn fades as we descend, replaced by the faint glow of our instruments. Below the fractures, we enter the ice shell. This is not uniform ice, but a complex matrix of frozen water, salts, and pockets of slush and brine. The ice near the surface is cold and rigid, but as we descend, it gradually warms. The tidal flexing that heats the moon is concentrated here, where ice meets ocean. At a depth of perhaps 5 kilometers beneath the South Pole, we break through into liquid water. The ocean is dark, lit only by whatever faint bioluminescence might exist if life is present, or by our own lights. The water is salty, roughly comparable to Earth's oceans, and cold by human standards, though warmer than the ice above. We descend further, 10 kilometers, 15, toward the rocky core. The pressure increases, the temperature rises, and then we see them. Hydrothermal vents. Chimneys of mineral deposits rise from the sea floor, spewing dark, mineral-rich water into the surrounding ocean. The water shimmers with dissolved chemicals, hydrogen sulfide, methane, hydrogen, and a complex soup of organic molecules. The temperature at the vent mouths may exceed 100 degrees Celsius, maintained by pressure despite being well above water's normal boiling point. On Earth, hydrothermal vents host thriving ecosystems. Tube worms, crabs, shrimp, fish, and countless microorganisms cluster around the vents, drawing energy from the chemical reactions rather than from sunlight. These communities are completely independent of photosynthesis. They represent an alternative pathway for life, one that could operate on any world with water, rock, and heat. The discovery of hydrothermal vent ecosystems on Earth was itself revolutionary. Before 1977, scientists assumed all life on Earth ultimately depended on sunlight. Plants capture solar energy through photosynthesis. Herbivores eat plants, carnivores eat herbivores, and decomposers recycle the remains. Even deep-sea creatures, living in perpetual darkness, were thought to depend on organic matter raining down from the sunlit surface. Then, in February 1977, geologists exploring the Galapagos Rift in the submarine Alvin discovered something extraordinary. Around vents spewing superheated water from the seafloor, they found dense communities of giant tube worms, clams, and crabs. The water temperature near the vents exceeded 300 degrees Celsius, far hotter than any known habitat. How could life thrive here, 2 kilometers below the surface, in total darkness, at crushing pressures? The answer was chemosynthesis. Bacteria at the base of these ecosystems were using chemical energy rather than light energy. Hydrogen sulfide, spewing from the vents, served as their fuel. They oxidized it to sulfate, capturing the energy released to build organic molecules from carbon dioxide. These bacteria were the primary producers, the foundation of an entire ecosystem independent of the sun. The discovery transformed our understanding of life's possibilities. If life could thrive at hydrothermal vents on Earth, it could potentially exist anywhere with similar conditions: liquid water, dissolved chemicals, and a source of heat. Over the following decades, scientists found vent ecosystems throughout Earth's oceans. The Mid-Atlantic Ridge, the East Pacific Rise, the Indian Ocean, and even beneath Arctic ice. Everywhere hot water met cold ocean, life flourished. They also discovered diversity. Different types of vents supported different communities. Black smokers, spewing superheated water laden with metal sulfides, had one set of species. White smokers, with cooler alkaline fluids, had another. Lost City, a field of carbonate towers in the Atlantic, hosted yet another ecosystem. This one powered by hydrogen from serpentinization rather than sulfur from volcanic activity. Lost City is particularly relevant to Enceladus. The towers there form from reactions between seawater and mantle rock, producing hydrogen and methane. The temperatures are moderate, around 90 degrees Celsius. The chemistry is dominated by carbonates rather than sulfides. This environment may be more similar to what exists on Enceladus than the classic black smoke events. Could similar communities exist on Enceladus? We must be careful here. There is no direct evidence for life on Enceladus. No organism has been detected. No unambiguous biosignature has been found. What we have is a plausible environment, a place where life as we understand it could potentially survive. Let us examine the requirements for life and evaluate how Enceladus measures up. First, life needs liquid water. Enceladus has a global ocean that has existed for geological ages. This requirement is clearly met. Second, life needs chemical building blocks. The plumes contain organic molecules, including complex compounds with multiple carbon atoms. Carbon dioxide, ammonia, and other potential feedstocks for metabolism are present. The ocean is in contact with a rocky core that can provide additional minerals and nutrients. This requirement appears to be met. Third, life needs an energy source. On Earth, most life ultimately depends on sunlight, but chemosynthetic organisms at hydrothermal vents demonstrate an alternative. The hydrogen detected in the plumes could power methanogenic metabolism. The chemical gradients at hydrothermal vents could support a variety of other metabolic strategies. This requirement is potentially met. Fourth, life needs stability over time. Origins of life chemistry requires consistent conditions over thousands or millions of years for complex molecules to accumulate and organize. Enceladus's ocean has probably existed for much of the Moon's history, providing ample time for prebiotic chemistry or the origin of life. This requirement appears to be met. By these criteria, Enceladus scores remarkably high as a potentially habitable world. But potential is not proof. The strongest argument for life on Enceladus is the detection of hydrogen and the inference of hydrothermal activity. On Earth, wherever we find liquid water in contact with rock and a source of chemical energy, we find life. No exception has been discovered, despite decades of searching in the most extreme environments on our planet. Deep gold mines in South Africa, where temperatures exceed 60 degrees Celsius and no sunlight has penetrated for millions of years, contain bacterial communities. Frozen lakes beneath the Antarctic ice sheet, isolated for hundreds of thousands of years, contain microbial life. Acidic hot springs, alkaline soda lakes, salt flats, and deep-sea sediments all harbour organisms. If life can exist anywhere conditions permit on Earth, perhaps the same is true elsewhere. Perhaps wherever the conditions of Enceladus are met, liquid water, chemical energy, and time, life arises. This is the optimistic view, and it has serious scientific defenders. The pessimistic view notes that we have only one example of life arising, Earth. We do not know how probable the origin of life actually is. Perhaps it requires conditions so specific that Earth-like environments are necessary. Perhaps it requires chance events so improbable that it happens only once per galaxy or less. We simply do not know. The only way to resolve this uncertainty is to look for life elsewhere and see what we find. This is why Enceladus is so exciting. It is not just potentially habitable, it is accessible. Unlike Europa, whose ocean lies beneath perhaps 25 kilometers of ice, Enceladus is venting its ocean into space. We do not need to drill through kilometers of frozen crust to sample the water. We just need to fly through the plumes and analyze what we collect. Cassini demonstrated that this is possible. A future mission with more sophisticated instruments could search directly for biosignatures, complex organic molecules inconsistent with abiotic chemistry, isotopic ratios characteristic of biological processes, or even cells or cellular components. Several missions have been proposed. The Enceladus Life Finder, or ELF, was a concept studied in the 2010s. It would have been a flyby mission, passing repeatedly through the plumes with instruments designed specifically to detect signs of life. ELF would have measured amino acids and their chirality, the handedness of their molecular structure. On Earth, life uses almost exclusively left-handed amino acids. A sample containing predominantly left-handed or right-handed amino acids would be strong evidence of biological origin. ELF was not selected for funding, but the concept influenced later proposals. The Enceladus Orbilander, studied more recently, is a more ambitious concept. It would orbit Enceladus, flying through the plumes multiple times to collect and analyze samples, then eventually land near one of the tiger stripes to study surface deposits. A lander could examine plume material that has fallen back to the surface, potentially in higher concentrations than what can be collected during flybys. Other concepts include sample return missions, which would collect plume material and bring it back to Earth for analysis in terrestrial laboratories. Such missions would be complex and expensive, but they would allow the full arsenal of analytical techniques to be applied to the samples. The European Space Agency has considered Enceladus missions as well. Japan's space agency, JAXA, has expressed interest. China has ambitions in the outer solar system that could potentially include Enceladus. Yet as of now, no mission to Enceladus is funded and in development. The scientific community recognizes its importance, but space exploration budgets are limited, and competition with other worthy targets is fierce. Europa, Jupiter's moon, often takes priority in discussions of ocean world exploration. NASA's Europa Clipper mission, launched recently, will study that moon in detail. The European Space Agency's JUICE mission is en route to the Jupiter system, but Europa's thicker ice shell makes direct sampling of its ocean more difficult than at Enceladus. The comparison between Enceladus and Europa illustrates the trade-offs involved in ocean world exploration. Europa is larger, with a diameter of about 3,100 kilometers compared to Enceladus's 500. Its ocean is correspondingly larger, containing perhaps 2 to 3 times as much water as all Earth's oceans. The greater volume means more potential habitat and, perhaps, more opportunity for life to arise and diversify. Europa also has a more energetic environment. Jupiter's powerful magnetic field accelerates charged particles to high energies, bombarding Europa's surface with radiation. This radiation is damaging to life on the surface, but it also drives chemical reactions that produce oxidants like oxygen and hydrogen peroxide. These oxidants could potentially reach the ocean and provide additional energy for metabolism, supplementing whatever chemical energy is available from the sea floor. However, Europa's ice shell is much thicker than Enceladus's, perhaps 15 to 25 kilometers. There are no confirmed plumes shooting material into space, though some observations have hinted at possible sporadic activity. Sampling Europa's ocean would require either drilling through kilometers of ice or finding rare surface deposits of ocean material. Enceladus, by contrast, offers direct access. The plumes eject ocean water continuously in a predictable location at velocities that allow spacecraft to fly through safely. The ice shell at the South Pole is only a few kilometers thick. Any future lander could potentially access ocean material without massive drilling equipment. The energy situation is less favorable on Enceladus. There is no equivalent of Europa's radiation-driven chemistry. The available energy is primarily chemical, from reactions at the ocean-rock interface. This may support only a sparse microbial ecosystem, rather than the potentially more vigorous biosphere that Europa's oxidants might enable. Which target is more likely to harbour life? Which is more accessible? Which would provide more definitive answers? These questions have no clear answers, and reasonable scientists disagree. Some scientists argue that Enceladus should be the priority, precisely because it offers easier access to subsurface water. Why struggle to reach Europa's ocean when Enceladus is spraying its ocean into space? Others counter that Europa is larger, older, and potentially more likely to host complex life if life exists at all. The debate continues. Regardless of which target comes first, the exploration of ocean worlds is one of the great scientific priorities of our time. Within the next few decades, we will almost certainly have much better data on the habitability of Enceladus, Europa, and perhaps other moons as well. While we wait for future missions, scientists continue to analyze Cassini data and develop new models of Enceladus's interior. One intriguing question is the age of the ocean. Has liquid water existed beneath Enceladus's surface for billions of years, since the early solar system? Or is the ocean a more recent phenomenon, perhaps only hundreds of millions of years old? The answer matters for the prospect of life. The origin of life on Earth took at least a few 100 million years, possibly longer. If Enceladus's ocean is young, there may not have been time for life to arise. If it is old, the odds improve significantly. Several lines of evidence suggest the ocean is ancient. First, the orbital dynamics of the Saturn system indicate that the tidal heating mechanism has operated for billions of years. Enceladus's resonance with Dione, which drives the tidal flexing, is a stable configuration that formed early in the system's history. Second, the differentiated structure of Enceladus, with a rocky core surrounded by water and ice, suggests it formed hot and has maintained internal activity ever since. If the Moon had ever frozen solid, it would be difficult to restart the differentiation process. Third, the chemistry of the plumes implies long-term interaction between water and rock. The salts and silica detected by Cassini could only form through extended geological processes. Most models suggest the ocean has existed for at least 1 billion years, and possibly for the entire 4.5 billion year history of the solar system. If so, life has had ample time to arise. Another question is whether Enceladus could have exchanged material with other worlds. When impacts strike a planetary body, They can eject material into space. If this material is not moving too fast, it can remain in orbit around the parent planet, eventually falling back or landing on other moons. Material ejected at higher speeds can escape into interplanetary space and potentially reach other worlds entirely. Calculations suggest that material ejected from Enceladus by impacts can reach other moons of Saturn, including Titan and Mimas. More intriguingly, material from early Enceladus might have reached the inner solar system, including Earth. This raises the speculative but fascinating possibility of panspermia, the transfer of life between worlds. If life arose on Enceladus early in solar system history, could it have seeded Earth? Or could life from Earth have reached Enceladus? Most scientists consider this unlikely. The journey between worlds is harsh, exposing any life to vacuum, radiation, and extreme temperatures for millions of years. The odds of survival seem low. But some microorganisms on Earth, particularly bacterial spores, can survive remarkably extreme conditions. They have been revived after hundreds of millions of years of dormancy. They can tolerate massive doses of radiation. They can survive impacts that would pulverize rock. We cannot rule out the possibility that life, if it exists on Enceladus, shares a common ancestor with life on Earth. We also cannot rule out the possibility that life arose independently on both worlds. Only by studying Enceladian life, if it exists, can we answer this question. The stakes are profound. If we discover life on Enceladus that uses the same fundamental biochemistry as Earth life, the same genetic code, the same amino acids, we will have evidence of panspermia. Life would have originated once and spread. If we discover life with different biochemistry, we will have evidence that life can arise independently more than once. This would suggest that life is a common phenomenon in the universe, emerging wherever conditions permit. Either answer would transform our understanding of our place in the cosmos. Enceladus is part of a larger story, the emerging realization that ocean worlds may be common throughout the universe. In our own solar system, we now know or suspect that subsurface oceans exist on Europa, Ganymede, Callisto, Titan, Enceladus, and possibly Pluto, Triton, and other bodies. Some of these oceans may contain more liquid water than all of Earth's oceans combined. The traditional habitable zone, the region around a star where liquid water can exist on a planet's surface, now seems like just one possibility among many. Water can remain liquid far from any star, heated by tidal forces, radioactive decay, or primordial heat. Moons of gas giants, dwarf planets in the outer solar system, and rogue planets drifting through interstellar space could all potentially harbour subsurface oceans. If this is true, habitable environments may be far more common than we thought. Every star may be surrounded by dozens of icy bodies with hidden seas. The galaxy could be teeming with ocean worlds. This has implications for the search for extraterrestrial life. Traditional efforts focus on detecting biosignatures in the atmospheres of Earth-like planets orbiting in stellar habitable zones. Such planets can be studied remotely through transit spectroscopy and other techniques. But subsurface ocean worlds are invisible to these methods. Their oceans leave no atmospheric signature. Their potential biospheres are locked beneath kilometers of ice. We could survey 1,000 planetary systems and miss all the life hiding within frozen moons and dwarf planets. This is not an argument against searching for life on Earth-like planets. It is an argument for expanding our search to include the ocean worlds that may be everywhere. Enceladus represents a test case. If we can detect life there, using spacecraft that fly through plumes or land on the surface, we will have proven that life can arise and persist in subsurface oceans. This would justify the effort and expense of exploring similar worlds throughout the solar system and beyond. If we search thoroughly and find no life on Enceladus, despite its seemingly favorable conditions, we will have learned something important about the difficulty of life's origin. Perhaps liquid water and chemical energy are not enough. Perhaps some other factor, something we have not yet identified, is required. Either result advances our understanding, but finding life would be the more exciting outcome by far. Let us consider what life on Enceladus might look like. If organisms exist in the ocean, they are almost certainly microbial. There is no reason to expect complex multicellular life in an environment where energy is scarce and conditions are extreme. The parallel on Earth is the deep biosphere, the communities of bacteria and archaea living in sediments, rocks, and water kilometers below the surface. These deep Earth organisms are slow living by surface standards. With limited energy, they cannot afford rapid metabolism. Some may divide only once per century, compared to bacteria on the surface that can divide every 20 minutes. Their populations are sparse, their activities subtle. Life on Enceladus would likely be similar. The available energy, primarily from chemical reactions at hydrothermal vents, would support only a limited biomass. Organisms would cluster near energy sources, leaving most of the ocean essentially lifeless. The most probable metabolisms would be those that exploit the chemicals we know are available. Methanogens, which combine hydrogen and carbon dioxide to produce methane, are a prime candidate. Such organisms are ancient on Earth, arising early in the history of life, and they thrive in environments without oxygen. Other possibilities include sulfur-metabolizing organisms, if sulfur compounds are present, and iron-oxidizing bacteria, if dissolved iron is available. The diversity would depend on the chemical composition of the ocean, which we do not yet know in detail. What would Enceladian organisms look like under a microscope? Probably not very different from Earth microbes. The fundamental constraints of physics and chemistry apply everywhere. Cells need membranes to separate their internal chemistry from the environment. They need information storage molecules to pass on their characteristics to descendants. They need enzymes to catalyze reactions. Whether Enceladian life would use DNA, RNA, and proteins like Earth life is unknown. It might use completely different molecular systems. Or it might use the same ones, if there is deep commonality to life's chemistry, or if life on both worlds shares a common origin. One particularly intriguing possibility is that Enceladian life might be detected not by finding cells, but by finding the chemicals they produce. On Earth, life leaves distinctive signatures in the chemistry of its environment. Ratios of carbon isotopes are altered by biological processes. Certain organic molecules, like some lipids and amino acids, are produced almost exclusively by organisms. Gases like methane and oxygen can be produced abiotically, but certain combinations are hard to explain without life. Cassini already detected methane in the plumes. Is this methane biogenic, produced by methanogens? Or is it abiotic, produced by reactions between water and rock? The measurements were not precise enough to tell. Future missions with more sensitive instruments could potentially answer this question. If the methane has isotopic ratios characteristic of biological production, or if it is accompanied by other telltale chemicals, we would have strong circumstantial evidence for life. This kind of indirect detection might come before any direct observation of cells or organisms. We might have reason to believe life exists on Enceladus long before we can prove it by imaging a microbe. Let us now turn to the practical challenges of exploring Enceladus. The Saturn system is far from Earth. Cassini took 7 years to arrive, even with gravity assists from Venus, Earth, and Jupiter. Future missions would likely take similar times, though advanced propulsion systems could potentially shorten the journey. Once at Saturn, a spacecraft must navigate to Enceladus's orbit and either fly past, enter orbit, or land. Each option has trade-offs. Flyby missions are the simplest and cheapest. The spacecraft passes through the plume system at high speed, perhaps 10 kilometers per second, collecting samples during the brief encounter. The advantage is simplicity. The disadvantage is limited collection time and the possibility that high-speed impacts could destroy delicate organic molecules or cells. Orbital missions provide more opportunities to fly through the plumes and can adjust their trajectories based on early results. However, entering orbit around Enceladus is challenging because the Moon's gravity is very weak. The spacecraft would likely orbit Saturn and make repeated close passes. Landing missions offer the possibility of studying plume deposits on the surface, where material ejected by the geysers falls back and accumulates. A lander could analyze samples at leisure without the limitations of a high-speed flyby. But landing on an icy moon 1 billion kilometers from Earth is extraordinarily difficult. Sample return missions would bring plume material or surface samples back to Earth for analysis in terrestrial laboratories. This would allow the most sophisticated instruments to be applied, including techniques that cannot be miniaturized for spacecraft. But sample return adds enormous complexity and cost, and there are concerns about planetary protection, the risk of contaminating Earth with extraterrestrial organisms, or vice versa. Planetary protection is a serious consideration for any mission to Enceladus or other potentially habitable worlds. The concern works in both directions. Forward contamination refers to Earth organisms hitching a ride on spacecraft and surviving on the target world. If hardy Earth microbes reached Enceladus and thrived, they could confuse future searches for native life. Even worse, they might outcompete or destroy any indigenous organisms, representing an ethical catastrophe of cosmic proportions. Backward contamination refers to extraterrestrial organisms reaching Earth in returned samples. Science fiction has explored this scenario many times, usually with apocalyptic results. The reality is more nuanced but still concerning. An alien organism might be incompatible with Earth life and harmless, or it might find our planet's biosphere a fertile environment with no natural defenses against it. International treaties require that spacecraft missions minimize the risk of contamination. Missions to potentially habitable worlds must be sterilized to rigorous standards. The exact requirements depend on the destination and mission type. Cassini's final dive into Saturn was partly motivated by planetary protection. With propellant running low, there was a risk that the spacecraft might eventually crash on Enceladus or Titan in an uncontrolled manner. By deliberately destroying Cassini in Saturn's atmosphere, mission controllers ensured that no Earth organisms would reach these moons. For sample return missions, the requirements are even stricter. Samples from potentially habitable worlds would need to be contained in multiple layers of protection during the return journey. Upon arrival at Earth, they would be received by specially designed laboratories capable of containing unknown biological hazards. Analysis would proceed cautiously, with extensive testing before any release of material to general laboratories. Some scientists argue that the risks of backward contamination are overblown. Any Enceladian organism would be adapted to conditions radically different from Earth. It would be unlikely to survive, let alone thrive in our biosphere. The concern, they suggest, is more science fiction than science. Others respond that we cannot predict the behavior of organisms we have never studied. The safest approach is extreme caution. Given the potential consequences of getting it wrong, prudence is warranted. These debates will intensify as sample return missions move from concept to reality. The scientific value of returning samples is immense. The risks are probably small, but not zero. Balancing these considerations is a challenge that planetary scientists, policymakers, and the public will face in the coming decades. Each approach has advocates, and the optimal strategy may involve multiple missions with different objectives. Power is a significant challenge for any Enceladus mission. Solar panels are impractical at Saturn's distance, where sunlight is about 1% as intense as at Earth. Radioisotope thermoelectric generators, or RTGs, are the proven alternative, converting heat from decaying plutonium-238 into electricity. But production of plutonium-238 is limited, and supplies must be shared among competing missions. Communication is another challenge. At Saturn's distance, radio signals take about an hour to reach Earth. Real-time control is impossible. Spacecraft must operate autonomously, making decisions based on pre-programmed instructions and their own sensors. The environment around Enceladus is relatively benign compared to some other targets. Radiation levels are much lower than at Europa, where Jupiter's intense magnetic field creates a punishing radiation environment. This makes Enceladus more accessible for electronic systems and potentially for preserving biological samples. Despite these challenges, Enceladus exploration is technically feasible with current or near-term technology. What is needed is funding, political will, and patience. Cassini's mission ended on September 15, 2017. After 13 years orbiting Saturn, the spacecraft was running low on propellant. Rather than risk an uncontrolled crash that might contaminate Enceladus or Titan with Earth microbes, mission controllers deliberately sent Cassini into Saturn's atmosphere. The end came after a series of daring maneuvers called the Grand Finale. Beginning in April 2017, Cassini dove repeatedly through the gap between Saturn and its innermost rings, a region no spacecraft had ever visited. Each dive brought new data about Saturn's interior, its magnetic field, and the mass and composition of the rings. 22 times Cassini threaded this needle, passing within 2,000 kilometers of Saturn's cloud tops. The spacecraft was moving so fast that a collision with a ring particle could have been catastrophic. But careful analysis of Voyager data and Cassini's own observations suggested the gap was relatively clear. The gamble paid off. On its final orbit, Cassini turned its antenna toward Earth and began transmitting in real time. The spacecraft entered Saturn's atmosphere at a latitude of about 10 degrees north, traveling at over 30 kilometers per second. Friction heated the spacecraft rapidly. For about a minute, Cassini continued to transmit, its thrusters fighting to keep the antenna pointed at Earth. The spacecraft measured the composition of Saturn's atmosphere, finding less helium than expected, and detecting complex organic molecules in the upper layers. Then the signal wavered. The thrusters could no longer compensate for atmospheric drag. Cassini began to tumble. The transmission cut off at 7:55 a.m. Eastern Time, when Cassini was about 1,500 kilometers above Saturn's cloud tops. The The spacecraft continued to fall, breaking apart and vaporizing in Saturn's atmosphere. Its atoms, including those that had once been assembled into instruments in clean rooms on Earth, became part of Saturn forever. It was a bittersweet moment. Cassini had been one of the most successful planetary missions ever flown, transforming our understanding of Saturn, its rings, and its moons. Its discovery of Enceladus's plumes and ocean was perhaps its greatest achievement, opening an entirely new chapter in the search for life beyond Earth. Scientists and engineers who had devoted decades to the mission gathered to watch the final signal. Many wept. They were saying goodbye not just to a machine, but to a companion, a remote extension of human senses that had shown them wonders beyond imagination. The data Cassini collected will be analysed for decades. Many discoveries remain to be extracted from the terabytes of measurements stored in archives. The spacecraft is gone, but its legacy continues. Now the torch passes to future missions. Whenever they launch, whatever they find, they will build on the foundation Cassini created. The question of life on Enceladus connects to some of the deepest questions humans have ever asked. Are we alone in the universe? Is life a cosmic inevitability, arising wherever conditions permit? Or is Earth a fluke, a singular spark of consciousness in an otherwise dead cosmos? For most of human history, these questions were the province of philosophy and religion. Now they are becoming questions of science. We have the technology to search for life on other worlds. We know where to look. What remains is to look. Enceladus is one of the most promising places to begin. A small moon with a big ocean, spraying samples into space for us to collect. If life can exist there, it is waiting to be discovered. If it cannot, that too is a profound answer. The ancient Greeks named this moon after a giant buried beneath a volcano, whose struggles caused the earth to shake. They could not have known how apt the name would prove. Enceladus is indeed a world of fire and ice, where internal forces drive plumes that shake the very boundaries of what we thought possible. Somewhere beneath that icy shell, in the darkness of an alien ocean, hydrothermal vents may be pumping heat and chemicals into the water. Perhaps around those vents, or elsewhere in the depths, something is living. Something that has never seen the sun. Something that does not know we exist. Perhaps one day we will meet. Perhaps a probe from Earth will descend through the tiger stripes, pass through the ocean, and shine a light on whatever waits below. Perhaps the first extraterrestrial life we encounter will be drifting in the currents of a frozen moon 1 billion kilometers from home. Or perhaps we will find nothing but chemistry, beautiful and complex, but not alive. That too would tell us something about our universe and our place in it. Either way, the search is worth making. Enceladus has given us a gift, a window into a hidden ocean, a chance to ask the ancient question with new tools. We would be foolish not to look. The geysers continue to erupt, the plumes rise and fall, the ocean waits. Let us consider what the next decades might bring. If current trends continue, the first dedicated Enceladus mission could launch in the late 2030s or early 2040s. It would arrive at Saturn roughly a decade later, in the 2040s or 2050s. The mission would spend several years studying Enceladus, flying through plumes, possibly landing, transmitting data back to Earth. By the middle of this century, we may have a definitive answer about whether life exists on Enceladus. We may know the composition of its ocean in detail. We may have images of its seafloor, its hydrothermal vents, its ice shell from within. If life is found, it will be one of the most significant discoveries in human history. We will know that Earth is not unique, that life is a cosmic phenomenon. The philosophical, religious, and scientific implications will reverberate for generations. If life is not found despite thorough searching, we will have learned that habitable conditions are not sufficient for life to arise. The origin of life may require special circumstances that Enceladus lacks. Earth may be rarer than we hoped. There is a third possibility: ambiguous results. Perhaps we will find organic chemistry that might be biological or might be abiotic. Perhaps isotopic ratios will be suggestive but not conclusive. Perhaps we will need further missions, more data, decades more study to reach a firm conclusion. Science often proceeds this way, through accumulating evidence rather than definitive single experiments. The search for life on Enceladus may be a long journey rather than a single discovery. Whatever happens, the exploration of Enceladus represents something remarkable about human civilization. We are a species that evolved on the African savanna, adapted for hunting, gathering, and social living. Yet we have built machines capable of traveling billions of kilometers, surviving the vacuum of space, and analyzing the chemistry of alien oceans. This is not inevitable. There is no law of nature requiring intelligence to explore the cosmos. We do it because we are curious, because we want to understand, because we find beauty in knowledge. These are among the finest qualities of our species. Enceladus does not care whether we visit. The plumes will erupt whether or not human instruments fly through them. The ocean will remain whether or not we ever understand it. But we care. We want to know. That wanting is precious. It drives the engineers who design spacecraft, the scientists who analyze data, the policymakers who allocate funding, and the public whose taxes support exploration. It connects us across nations and generations, a shared project of understanding that transcends our divisions. The tiger stripes glow faintly with heat against the frozen surface. Water sprays into the black sky. Saturn hangs overhead, its rings a glittering arc. Somewhere, perhaps, in the darkness below, something is alive, waiting, unknowing. We are coming.